Hello, and welcome to our video on the pH scale and pH buffers. So the pH scale is a scale that measures how acidic and how basic a solution is. And so the first thing I want to point out is a pH of 7 is neutral. So again, if our pH equals 7, that means it's neutral. And we expressed in a previous video, this is another way of saying that we have equal concentrations of hydronium and hydroxide in our solution. So the hydronium and the hydroxide completely balance each other out. Now, if we have a pH that's less than 7, our solution is going to be acidic. And so this is actually contrary to popular misconception. So a lot of people sort of think that a high pH value means that something's acidic. And it's actually the opposite. A low pH value means that something's acidic. And the lower the pH value, the more acidic it is. So we can look at, we have something sort of slightly acidic, like milk or coffee, versus a solution of a strong acid like HCl is going to have a much lower pH. And that means, of course, the greater the pH, the more basic the solution. And so, if we have something just a little bit above 7, like blood is a good example, that means that we're just slightly basic, or we can be all the way down here where we have a solution of a very strong base. It's going to be extremely basic. So how do we measure pH? Well, there's a few ways of doing it. In a lab, people often use a pH meter, but there's some other really easy ways to do it as well. So we'll often see in labs these little pH strips right here. So they're basically just little pieces of paper that have been treated with chemicals, and when you dip them in a solution, they change color, and that reveals the pH. And so they'll come in these little containers with a color scale there, and so you just match up the strip once you dip it in the solution to the color on there, and you can get a rough idea of the pH. It's not nearly as accurate as the pH meter, but heck, these are really cheap and really portable. And then finally, we can also use what's known as an indicator. So we use this in titrations. We mentioned indicators in the titration, but certain indicators we can actually use to measure pH more accurately, because we'll end up with a variety of colors. And so one of the more interesting ones is it's derived from cabbage, actually. So here's a natural indicator that occurs in cabbage, and we can get a variety of different colors depending on the pH of our solution. Just a few different methods. So how do we calculate pH? Well, pH is a measure essentially of how acidic or how basic something is, and pH is going to equal the negative log of our concentration of hydronium. I know I said a dirty word in a class like this, logarithm, but you're going to have to do some logarithm calculations in this class. So one thing we should touch upon is sig figs. So usually our concentration of hydronium will be expressed in some sort of scientific notation, and so our coefficient is going to tell us how many sig figs we have. So our top number has 1 sig fig here, and then these others have 2 sig figs. And in our pH value, that's going to dictate how many decimal places. So if we have 1 sig fig in our concentration of hydronium, that's going to mean 1 decimal place in our pH value. And if we have 2 sig figs in our hydronium value, that's going to mean 2 decimal places in our pH. And I can explain the reasons why, but I probably don't need to get into it. That might make it more confusing for you guys. But suffice it to say, coefficients, the sig figs in your concentration of hydronium become decimal places in your pH value. So here we have an example problem. Find the pH of a solution with a hydronium concentration of 1.7 times 10 to the negative third. So we're going to have to use a calculator for this, scientific calculator. We're going to say our pH is equal to the negative log of our concentration of hydronium, which is 1.7 times 10 to the negative third, and we end up with a value of 2.77. And this might be a great time to test to make sure that you're able to do this calculation correctly. Make sure that when you take that log, you take it of both the 1.7 and the 10 to the negative third, and see if you can agree with this value right here. And as mentioned, our sig figs become decimal places in our pH value. And so the other thing we might be asked to do is convert from pH into concentration of hydronium. And the equation that we use to do this is our concentration of hydronium equals 10 to the negative pH. And so again, you'll need a calculator to do these calculations typically. So for 825, our concentration of hydronium is going to equal 10 to the negative 8.25. We crunch our numbers here, we end up with a hydronium concentration of 5.6 times 10 to the negative 9th. And notice here that we have 2 decimal places in our pH, so that's going to become 2 sig figs in our concentration of hydronium right here. So fantastic work so far, guys. I'd like you to now pause the video and please complete questions 1 through 5. All right, welcome back. Let's move on to our final topic of the chapter. And the final topic of the chapter is what's known as buffer solutions, or buffers. And so buffers are going to contain an acid and a base, and we'll explain more about that later. But essentially, they're going to be able to absorb and neutralize any added acid or any added base. And these are going to be incredibly important to keep cellular pH steady, because if the pH of a cell changes, then that's going to affect all the enzymes and proteins, and then the organism will die if that pH changes. So these buffers are super duper important to biological systems. And so our body actually has buffer systems that are going to keep our blood pH really close to 7.4. And this is going to be really important because if that pH changes, then it's going to disrupt our structure of our proteins and our structure of our enzymes, and we can die if our pH changes too much. These buffers are really important. And our lungs and our kidneys and several other organs are responsible for helping to maintain our blood pH. But I picked the kidney picture here because I thought that Hello Kidney was funny, but also because our kidneys actually will expel some of the components of our blood out into our urine in order to keep that pH steady. And we'll talk more about this later on. So if we look at a buffer and a solution that's not a buffer, so let's start out with a solution that's not a buffer. If we take some water, regular old water, and if it's pure, its pH is 7.0. And if we add even a tiny amount of strong acid to it, our pH is going to drop dramatically, down in this case to a pH of 4. Or if we add even a small amount of base to it, again, our pH is going to shoot up dramatically. So if we take pure water, what we see is that the pH is going to be very quickly shifted if we add any sort of strong base or strong acid whatsoever. Now if we take a buffer solution now, this buffer solution also has a pH of 7. If we add a strong acid, our pH changes, but now just slightly. So maybe for the same amount of acid changed, we just go down just a tiny bit to a pH of 6.9. So we have this minimal amount of change here. And maybe if we add just a little bit of base, same amount as we did before, now we go up to 7.1. So we still change in pH somewhat, but the pH shift has been radically minimized, radically diminished by this use of a buffer solution. So what is a buffer solution going to be made of? So a buffer solution is going to be one of two things. It's going to be a weak acid and its conjugate base, or a weak base and its conjugate acid. And so let's start out with the weak acid situation. So the weak acid, if we have that mixed with its conjugate base, any sort of base we add can be neutralized by that weak acid. And in a previous video, we talked about the fact that the weaker an acid, the stronger the conjugate base. And so that means for this weak acid, that conjugate base is actually going to be strong enough to neutralize any acid that we add. So if we add a base, our acidic component of our buffer will neutralize it. And if we add an acid, the basic component will neutralize it. And similar idea for the weak base. Weak base will neutralize any incoming acid, and the conjugate acid will neutralize any incoming base. And so this allows us to keep the pH relatively stable. And ideally, what we want is nearly equal concentrations of our weak acid and its conjugate base, the weak base and the conjugate acid. Alright, so here we have an example of a buffer solution. We are going to take our acetic acid, which is a weak acid, and mix it with a bunch of conjugate base. So in this case, we're going to use sodium acetate. Why sodium acetate? Well, the sodium is inexpensive, it's highly soluble in water and non-toxic, so this is ordinarily what people use. If you're making a buffer solution, people will use, again, the weak acid and usually the sodium salt of its conjugate base, because again, it's cheap, soluble, and non-toxic. So we mix these together, we end up with a buffer solution. The sodium ions are spectators, so we're going to ignore the sodiums. And so we end up with this buffer solution that's going to be a mix of our acetic acid as well as our acetate ions. And so this is going to keep our pH steady. So here is what happens if we add a base to our buffer solution. So we start out with equal concentrations of acetic acid and acetate. And if we add a base, we're going to lose some of our acetic acid because that's going to be used to neutralize the incoming base. And we're going to make a little bit more of our conjugate base here, a little bit more of our acetate ion. But our pH is only changed just slightly. And alternatively, if we add a bit of acid now, what we're going to see is it's going to react with our acetate. So we start out with equal amounts of acid and acetate. And if we add a strong acid now, it's going to consume and use up some of our acetate, and we're going to form more acetic acid. So our ratio has been skewed a little bit, but our pH is only going to change slightly because that strong acid's been consumed by the conjugate base. So here we have a diagram that shows both. We start out ideally, it's actually known as an ideal buffer when we have equal amounts of the weak acid and its conjugate base. And if we add something basic, we're going to use up a little bit of acetic acid and make a little bit more acetate. And if we add something acidic, we'll use up a little bit of our acetate and make more acetic acid. But the pH stays relatively steady. One thing I do want to mention, though, is notice that we do consume chemicals when we add acid or base. So eventually, if we add enough acid or base, the buffer will run out of component. It'll be all used up and sort of stop working. So excellent work. I'd like you guys to now end the video and please complete questions 6 through 12.